Okay. Electric cars would be nice, right? There's a problem, though, batteries. Space shuttle, it's retired, but again, another problem. You may not see it and know what it is, but rocket fuel, hydrogen gas. And you've seen me blow up hydrogen balloons. That's definitely rocket fuel, right? Now, whether it's an electric car they're trying to develop or rocket safe, it'd be nice to have a little sensor that recognizes hydrogen gas. If there's a leak, okay, you could be sitting in your car if they're using a fuel cell, or right, if you're an astronaut, you'd like to know if there's a leak. Well, right now NASA has got a hydrogen sensor, and however, it's an electric circuit. And as with all electric circuits, there's a potential for a little short, a little spark, and then in this case, it'd go boom. You don't want your little sensor to go boom. So one thing we've been working on is what's in this container. And in this container is our hydrogen sensor. And it's not electrically based, it's color. So the idea is you'll use fiber optics to sense when there's hydrogen gas present, because our little sensor here, compound, is going to change color. And inside, there's a bunch of ingredients in there. It's listed as reactants in green, because that's what kind of color is. I don't know, that's what I call it, green. And in that mess of reactants is platinum, and it's a catalyst. If I told you what all the other reactants are, I'd probably have to kill you. No. But that's the idea, because we're still working on this. So in the presence of hydrogen gas, our little sensor changes color, and then, you can have fiber optics can run anywhere. Space, temperature, huge drastic changes in environment. Fiber optics work great. So you can remotely sense things with fiber optics. So it could be in the car, on the space shuttle, rocket, International Space Station, wherever, right? Fiber optics is really the way to go for this kind of thing. So let me just show you. So first you have to recognize the color of this little sensor. All right? I don't know if you can see it way in the back, but it's kind of a green color. Okay? Here's hydrogen is heavier or lighter than air? Definitely lighter, right? Only H2. So if I want to transfer it into the container, I've got I'll invert it. Can you see the color change? What color is it now? I see a dark blue. But, color is, everyone sees a different color. So there's definitely a change. There's definitely a change. Okay? So yeah, it's blue. Blue. Now, what are all the quizzes? Pablo. This little potential energy diagram that I drew for the sensor, it exhibits an exothermic or endothermic reaction. Exo, definite, right? Because products are lower in energy. Well, kicked off a lot of heat. Okay. What would be the... Eddie, do you remember? What did I say was the catalyst in my little sensor? Platinum, right? It was platinum. Effect of a catalyst on this potential energy diagram. Lowers the technical jargon. You can say lowers the hump, it works. But it sounds a lot better to say what Nick said. Lowers the activation energy. Right. Okay. So there's some why as to why this stuff is a big deal. We've got some jargon, Jessica Rojas, and it's elementary reactions and reaction mechanisms. What's the difference? What's the difference? You're reading any of this stuff? Now, if you stick with this science stuff, you're going to take organic chemistry and reaction mechanisms. If you make any product, I think, ibuprofen, drugs, any commercial product, you definitely want to know this reaction mechanism. You want to know what's going on. What's the reaction mechanism? Everything we've talked about so far in general chemistry was just some overall reaction. We never used the word overall. We just said, hey, that's the reaction. That's what's going on. But how did the reactant actually get the product? First, there's this little step. Then there was this little step. Then there was this little step. Add up all the little steps. If you could figure out what they are, you're going to end up with the overall reaction. We've been messing with the overall reaction this whole time. We've never involved ourselves with the little steps. They will in organic chemistry. So the word for little steps in this case is what? The elementary reaction. Okay. What's actually going on at the molecular level? This molecule colliding with this molecule to generate something. Okay. Just like in this example we have. We've got two steps. First, A collides with B, makes C, and then C goes on to collide with A and make D. That's the reaction mechanism. We hardly ever see it, though. Instead, we just see the overall reaction. How would you write the overall reaction, Amanda? Well, add up all the reactants. Oh, she's combining the 2A. She sees the 2A. Okay, 2A. And good. Oh, careful. The C is going to be gone on you, right? And just going to generate D, right? Now, we could have wrote some math that it's not skipped the step and wrote A plus B plus C plus A gives C plus D, and then, combine like terms and things. But she's right. Okay.
So there's one on each side.
One on each side. Yeah. Okay. So we are used to the overall reaction, and that's this. Okay. But the overall reaction, heck, Matteo, what doesn't even show up in this something is really important. What doesn't even show up in the overall reaction? Yeah, C doesn't even show up. You don't even care. But if you're making ibuprofen, you want to know what's going on, what these intermediate things are. You want to monitor things, make things efficient, make sure you get what you want. Molecularity is another new word. Okay? The reason why they're getting into it, and molecule is key in this word, in molecularity, because these elementary reactions, that's exactly what's going on. This molecule in space, for example, in this elementary reaction, step 1, A molecule in space is actually colliding with a B molecule, and they got to be in the right orientation, with the right amount of energy, then they'll generate whatever C is. So if that's what's going on, what do you think this molecularity means? If I look at this first step, the number of molecules involved, you just say the molecularity of step 1 is how many molecules are involved to generate C? In step 2, right? Because 2 molecules are involved. You don't care about products. You just want to know how do you get there. So A is colliding with B. Right? And step 1 is 2. And step 2, it's still 2, isn't it? There's 2 molecules involved. So all molecularity, all it is just the number of molecules involved in that elementary reaction. Okay. Let's check out writing rate equations for elementary reactions. Notice they're not using the word rate laws anymore. They're using the word rate equations because they're talking about an elementary reaction. So it's, I don't know, they like to use the word rate equation. But it's the same thing. Okay, so write the rate equation for each elementary reaction below. So 2A going to be, it's just some step in a mechanism, and we want to write the rate law for it. So pretty much all you do, rate equals K, just like before, and then the concentrations of what's involved. since we know what the elementary step is, we know an A molecule collides with an A molecule. All that matters is the concentration of A, and A, right? All that matters is this A molecule. So really, we should write not 8. Okay, yeah, it looks better 8 squared. But that's all you do to write rate equations for elementary reactions. Just look at the reactants. Because at the molecular level, that's what's colliding. So you know the rate law just by looking at it. For example, Sylvia in B, how would you write the rate law for B? Good. Concentration of D times concentration of C. Exactly. Okay. Writing overall rate equations or rate laws, I like to use the word rate laws now, for a reaction mechanism. Okay? We have a step 1, we have a step 2. Oh, hey, I can try to confuse you some more here. I can give you the overall reaction. What did we say? We said it was 2A plus B gives D, right? That was my overall. Now, before, Genevieve, I think this was 2 class periods ago. If we wanted to determine the rate law, a bunch of what? What was that? What did these problems entail? Someone said it. I thought someone said the word. Experiments. Didn't they have to give us a whole bunch of experiments? All right, where they keep one constant, they double the other one, see what the effect was on the rate. And it was a lot of work to get these rate laws. So what that problem really was the overall reaction. They said, here's the overall reaction. Figure out the rate law. You had to do all these experiments. Not so if they give you the reaction mechanism. You know just by looking at the reaction mechanism what the rate law is. What is it going to be? And they even give you a hint. Which step is the bottleneck? The slow one, the very first one. Once this mechanism gets over the slow step, gets over the bottleneck, it's done. Because everything else is so fast. So the rate law for the entire mechanism is simply the rate equation for the slowest step. So it would just be A times B. A lot easier, right? But go back. This question could have been changed. They could have gave us the overall reaction, find the rate law. But they got to give us all these experiments. We figure it all out. We'll end up with what? Yeah, the rate equation for the slow step. We'll end up with the rate equals K times A times B. Concentration. Make sense? Okay. Catalysis. Ray, what catalyst was used in my little hydrogen sensor? It was what again? Start of the P. Platinum. It was platinum. Okay. So they like to put a little descriptor on these catalysts. They like to say, oh, that's a homogeneous catalyst. This is a heterogeneous catalyst. The key is if everything is in the same phase, it's homogeneous. If you have different phases involved in this little sensor, then it's going to be a heterogeneous catalyst. Right? Is the phase of the catalyst the same as in this little sensor I've got? Is the phase of the catalyst the same as, I don't know, the reactants or stuff? Now, there's some reactants in there that are solid. You can tell there's other stuff in there. But what else is also involved? Yeah, the hydrogen gas. So platinum, in this case, would be a what type of catalyst? Heterogeneous, exactly. Right? Because it's different phases are involved. Different phases from what the catalyst phase is. Okay. What is the molecularity? Let's do some problems here. Lewis. Yeah, where's Lewis? There he is, Lewis. I was thinking of a different Lewis. Lewis, what is the molecularity of A? I don't know how that oxygen atom got there, but it did. It must have been in some earlier elementary step that was generated, but what would you say the molecularity is of the elementary reaction in A? 5. Is it all of them, or is it just the reactant? Yeah, just whatever the left side is, just the reactant. So you have to have an oxygen atom, an oxygen molecule, and a nitrogen molecule colliding at the same instant in time, in the same spot in space, at the right orientation, and this thing will progress. So the molecularity is 3. In B, Jessica Vaughn, the molecularity is 2. You have a chlorine atom and this NO2Cl. Everybody, how about C? 2. And 1. Right. Okay. Not so bad. Write a rate equation for these elementary reactions. Mariella, how would you write a rate equation for A? Rate. Well, I'm so slow. Rate equals K times the concentration of CS2. How about the next one, Mallory? Yeah, methyl bromide. You'll see that in the next. Yeah. And I like how she's saying it. She's saying concentration. Those brackets are concentration. Okay. So, man, you got to be thinking by this point, this is a nice way to spend the last class period before our review. But you know things got to get ugly at some point, right? There it is. I think this is where it's going to get ugly. And what is the question about? The question is always, does the rate increase, decrease, or remain the same? And they're going to do all these things. And all you care about, there's a lot of verbiage here. All you care about is this. What is the rate equation? If what they're messing with doesn't influence anything in the rate equation, there's going to be no effect. If what you're doing in here decreases a concentration, well, then it's going to decrease the rate. If it increases the concentration of something, right, in the rate law, it'll increase the rate. That's the game you're going to play. Now, before we can play this particular game, though, Alexa, we have to recall what H3O plus is. We talked about this. We were talking about solvating, and we talked about it for about 5 minutes, and then we just... Do you remember? H3O plus. It's called hydronium. It's called a hydronium ion. Now, the reason why I'm saying this is because this is an H plus. Right? If you look at a hydrogen atom, how many electrons does it have? It has 1. So H plus is just a bare proton. And they know bare protons don't exist in water. And this whole time we've been writing H plus. It doesn't exist. Instead, that bare proton grabs onto a water molecule, and it's going to make the hydronium, H3O plus. So whether you write H plus or H3O plus, technically it's correct to write H3O plus. But just think if you did. Every single reaction we've done, we have to write H2O, right? on both sides to convert the H plus to H3O plus. It doesn't really matter. H2O is going to cancel on both sides. So it's a moot point. Forget it. Just use H plus forever. To this day, I've done this so much, though, that when I see H3O plus, I don't see H3O plus. I see H plus, because that's what it is. So when you see H3O plus, see H plus. That's what it is. It's H plus. Okay? Okay. So, I don't know why they did it, but we have to go through it because it's in the homework. So what we're doing in this very first example is we're adding, Victoria, sodium hydroxide. We're dumping some sodium hydroxide in here. Will that influence the rate? I agree with her at first glance. She says it wouldn't, because hopefully what she's looking at is she sees NaOH. All she does is she looks in the rate law. Does she see Na or OH? No. So you'd say, hey, no effect. But then life is never that easy. H plus interacts with OH. Remember, acid and base makes water. So you add OH, you're effectively decreasing which concentration? The H plus, the hydronium. You're decreasing its concentration because you're making it react up. You're sucking it out of there, right? You're making water. So by adding NaOH, you're decreasing the hydronium ion concentration. So what happens to the rate? Eddie, what happens to the rate? Decreases. Yeah. Okay. Nick, now what are they doing? Now they're dumping in a bunch of water. Oh, they're not adding H plus. They're adding more H2O. But remember, H2O is not, well, it's not charged. It's not H plus. It's not H3O plus. They're two totally different things. So, I mean, it's similar, but it's not the same thing. So they're not adding anything in the rate law. So again, my first guess would be it remains the same. But you got to think about it a little bit more. What do the brackets mean? Concentration.
You add water.
You add water. When you add water, it decreases concentration. What's the word for that? Dilution. You're diluting stuff, right? There's less stuff per unit volume. The rate's going to go down because those numbers went down. Those concentrations went down. So it decreased. You just diluted things. You made the concentrations lower. Pablo, we're going to add a catalyst. Someone did a bunch of work and they figured out a catalyst for this reaction and they dumped it in there and the rate does what? The rate will increase. But we're supposed to say why. We're supposed to say why. It lowers the activation energy. Yeah, you could say that, but it's not really what they're looking for. Because they want to mathematically, like everything in here has been math so far. Oh, this number, right? Or when we said that we added water, things were diluted, then we're saying that this number and this number got smaller. Okay? Now we're saying we added a catalyst. Well, what changes in the rate law? You can't change those guys. Their concentration. The only thing you do is mess with K. K is going to get what for a catalyzed reaction? K is going to get bigger. K is bigger. That's the only way it could happen. Okay? K gets bigger. Let's see. Amanda, the reaction is carried out at 15 instead of 25 degrees Celsius. So they made things a little bit colder. What would you guess? What's going to happen to the rate? Any influence? What's that? Increase? Decrease? Things are colder. Things are slower. They are. They have to be. So the rate should decrease. I agree with her. But you got to say why. If you mess with the temperature, is that going to influence the concentration of hydronium? No. You didn't add it or subtract. It's not going to mess with concentration. It's going to make K get smaller. K is smaller. Okay. One more question. See if you can remember how to draw a potential energy diagram for an uncatalyzed exothermic reaction. So remember what the axes were, right? Where you put the reactants and products. And once you get it drawn for an exothermic reaction, or something, indicate what changes if this reaction now becomes catalyzed. You add a catalyst. Okay. Go ahead and sketch in what you think it's going to look like. Well, you could say time. Time is okay, but it's not conventional. You should write reaction progress. And the reason why they like reaction progress is they spend a lot of energy and computing power on these things. They have these movies. And what actually is happening is you have these molecules moving together, getting closer and closer and closer. The reaction's progressing. Then they collide. They do their orientation thing. If they have the right energy, they turn into product. So they like the word reaction progress better. But okay. Now, I went to school with a guy who had a photographic memory, and I'm sure what he would have done in this case is to scroll back his memory and flip things back to this. Isn't that it? How would you draw in the dashed line for a change for a catalyst? What would you do? Anybody? Well, how would this... Now you have to draw and indicate what a catalyst is going to do to this. The activation energy? It's got to be smaller. Yeah, draw another little hump that is smaller. Something like that. Okay. Okay. So have a good day. Come by if you have some questions.